Hey gang, I'm going to talk about the major points from Chapter 5, the laws of motion. This is going to be really quick because you know so much about this already. We start with Section 5.1. You know that a force is a push or a pull. It could result from contact between objects, or it could involve force fields like gravity, or magnetism, or electrical charge, which creates forces. And we talked briefly before about the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But that doesn't entirely explain some things. For example, why if you push something with a solid object and you're pushing against another solid object, one solid object doesn't simply go straight through the other object. And to get into that, we say that matter is rigid because solid matter is rigid because of the electrical bonds in the matter. And that's a function of electromagnetic forces. But there's also electron degeneracy pressure. That is, an object can't penetrate through another object because not only are the molecules and atoms locked into a rigid structure, each particle in the structure takes up a certain amount of space, and according to the principles of the Pauli exclusion principle, you can't have two particles occupying any one quantum space. So electron degeneracy pressure you can think of as creating force or pressure, but it's ultimately traceable to electromagnetic forces holding matter together. We know that if the net force, or the sum of forces on an object, is zero, the acceleration is zero. And we say that the object is in equilibrium. You might have dynamic equilibrium, where the object is in constant straight line motion, or static equilibrium, in which the object is at rest. Okay. But if the summary of forces is not equal to zero, then there will be acceleration. Okay. Remember that force is a vector. You can have multiple forces working on one particular object, for example, in the tug-of-war problem we gave. And you have to add or sometimes subtract vectors to determine what the net force is. One thing to bear in mind is to have a force, you need to have two objects. If you have only one object, you could have a field, for example, a gravitational field or electrical field, but unless you actually have a second object, you can't have a force being created. Okay. You remember Newton's laws. Newton's first law is simply the law of inertia. Body at rest tends to remain at rest. Body in motion tends to continue in straight line motion. The second law has to do with the magnitude of acceleration caused by forces. Acceleration is directly proportional to the amount of force and inversely proportional to the amount of mass. Okay. Now, some books, including our book, Serway, speaks of inertial mass and gravitational mass. I like to just say mass. Mass has two main results. It causes gravity and it resists acceleration. But it's always the same measure of mass. You don't get a different measurement of mass whether you're talking about inertial mass resisting acceleration or gravitational mass creating gravity. Okay. Well, we can also speak of inertial reference frames. An inertial reference frame is any frame of reference that is not accelerating. So any reference frame that's moving at a steady speed is an inertial reference frame. And certain laws of motion apply to inertial reference frames and others apply to any reference frame. For example, the theory of special relativity applies only to inertial reference frames. By the way, Galileo understood the law of inertia before Newton is. Galileo rolled objects down ramps and understood that if there was no friction, objects rolling along a horizontal surface would continue to roll forever because of something that he didn't call inertia, but was like what Newton ultimately called inertia. Okay. Mass. It's good to understand what mass is. It's a property of matter that resists acceleration and creates gravity. And I talked about that a second ago. What's the difference between mass and weight? Weight is just the force of gravity, and it equals the mass times some gravitational field, little g. So as you can see by the arrows on top of the W and the G and the F, all of those are vector quantities. Gravitational field is definitely a vector quantity, so when you multiply a scalar mass by a gravitational field, you get a gravitational force. All right, Newton's second law. The sum of the forces equals mass times acceleration, or put differently, acceleration is directly proportional to force, inversely proportional to mass. Remember that the net force and the acceleration are always going to be in the same direction. If you know the direction of the net force, you know the direction of the acceleration. Okay, and there are some more ways to say what I just said. Remember the little symbol that looks like an infinity symbol or a Greek alpha. That is a direct relationship. 1 over alpha is a inverse relationship. And those are handy symbols to use on the AP exam to show without a lot of words that you understand that something's proportional or inversely proportional to something else. Okay. Well, in three-dimensional space, any vectors always have three components, which may be independent. So x, y, and z. As in free fall, we know that the acceleration, for example, caused by gravity, can operate in one dimension, like the y dimension, without having any effect whatsoever on the motion in the other direction. The acceleration, that is pointing one way, and it accelerates something only that way. Okay, I really strongly recommend looking at the quick quizzes in this chapter and working those out. And then I'm going to turn the page, and we will be over soon. Okay, one last point. You know the units of force are newtons. 1 Newton is a kilogram meters per second squared. It follows from F equals ma, F measured in newtons, m measured in kilograms, a measured in meters per second squared. That's all. So we've now covered the first 4 sections of Chapter 5.